In this video, we are going to look at decidable languages. In the last video, we know that a language is decidable if there is a Turing machine such that on any input, this Turing machine will always stop and it will accept this input if the input is in the language, and it will reject that input if that input is not in the language. Okay, so let me open up a whiteboard because that by definition, decidability is straightforward, but I want to point out the most important part of this concept. Okay, so what we really want to do here is that suppose you are given a language, let's call it L. And let me change color to different color, let's say blue. Okay. Okay, so let L be a language, and then you are given an input. So this is a language. And then you are given a string. So this could be a input. So any string. Any string. In the alphabet. Over the alphabet. Sigma. Okay, so this X could be, of course, we know that X could be in L, or X could also be not in L. So we want to determine which one is the case. So that's the question at hand. And then when we say that a language is decidable, it means that there is, so L is decidable. Oops. Means that there exists a Turing machine, M, such that on any string X, M on, now we take X as an input to M, so M on input X always halts. Okay, so we know that when M halts, it will end up at two possible states. One is the accept state, the other one is the reject state. Okay, so this halts and X. So if X is in A, so let me just write this one up. And if X is in L, not A, then M on X halts at N. Actually, it's only one at the accept state. If and if, otherwise, means that X is not in L, then rejects X. Okay, so the shorthand for this is really just that X is in L if and only if M accepts X. So when we say if and only if M accepts X, when it's decidable, this answer to this question is always given. There is always a solution, or there is always an answer. So this is different from the concept of Turing recognizability or Turing acceptability. So decidability means that I have this Turing machine on any string X. Okay, it takes X as its input. It holds. It will always hold. And when it holds, okay, we know that it will either it will either hold at an accept state or at a reject state. So by looking at which state it's in, then we know whether this X belongs to L or not, or in other words, if M accepts X, then X is in L. If M rejects X, then X is not in L, and M on X will hold at either an accept state, the accept state or the reject state. Okay, so that is what it means by a language to be decidable. Okay, now let's look at decidable problems for regular languages. Okay, so once again, so what we are looking at would be, because we know regular languages are languages accepted by DFAs, NFAs, and regular expression. So then, of course, for the DFA, for instance, the description of a DFA is a 5-tuple. You have a finite set of states. You have a finite set of alphabet. You have a finite definition of a transition, and you have an initial state of start state, and you have a set of accept states. So all of these can be represented as a binary string. For instance, we can simply use ASCII code to literally encode every symbol, including white space. Okay, so we have white space including punctuations and literally everything. So that then you have say this is your M, then you have a binary string that represents that M, because that binary string, when it's given to a Turing machine, the Turing machine needs to decode that encoding. So after decoding, you get all these parts back. Okay, so without loss of generality, from now on, we're going to use this notation, angle brackets, M comma X, to represent a coding of a Turing machine and of a object and a second object. So the first object would be either DFA, NFA, or regular expression, or some other things such as push-down automata, context-free languages, DFA, deterministic Turing machines, or non-deterministic Turing machines. Okay, so and also when we have a Turing machine, when we are presented with an encoding, we assume that that Turing machine has a decoder built in. So we don't explicitly mention decoding. Okay. So now then we can define 3 languages regarding regular languages. One is A sub DFA, which is a set of this input m comma x, where m is a DFA that accepts input x. And likewise, A sub NFA, so A represents acceptance, is a set of m comma x, where m is an NFA that accepts input x. A sub rex is a encoding of r comma x. R here is a regular expression that generates string x. Okay, so all of these 3 languages are regular because it's really straightforward to construct a Turing machine to determine whether this fact is true or not. Okay, so let's go. So for instance, if you are given an input, here's M is a DFA. So that really means that on a state diagram or any input X, okay, I will just run M on X. So in other words, I construct a Turing machine that simulates M on X, okay, because M has a transition, because that Turing machine can just runs that DFA as a program, and then on this input X, okay. So of course, DFA is just that if there is a path from the initial state. So let's say your X is X1, X2, up to Xn, where each SI is a symbol, is an alphabet symbol. If there is such thing, there's a path that ends in a substate, then this DFA, this Turing machine D accepts X, otherwise it rejects it. So in other words, after you finish reading your input X and it does not end at a substate, then this Turing machine D rejects it. So if M is an NFA, you can always convert it to a DFA using an algorithm first. Likewise, if your M is a regular expression, we know that we can always convert the regular expression to a DFA. So once you have a DFA, then checking whether a given input is accepted by the DFA is straightforward. Okay, just run that DFA. It ends if it ends at a substate, accepts it. Otherwise, rejects it. Okay, so next we look at a slightly more complex example. Well, just a slightly more. Okay, so let's say now my input is a DFA, which is just a description of that device. Of course, you can think of it as a program. I want to know whether this DFA or whether this program accepts some strings. Okay, so L of A is empty. So that means whether it doesn't accept anything. So that's easy to verify because as long as I'm given a DFA M, let's say you have a star state, a bunch of a substate. So what I want to know here is that for each of these substate, I want to see whether it is reachable from the initial state. If it is, that means it must accept something. Okay, so then I know that if there is such a path, I will reject that input, otherwise I accept it. So that means that I have a decider that on this, that decider always halts because it only checks that A, whether there is a path on that diagram, on this diagram of M, that was a set state that's reachable from the start state. For instance, you can use a breadth first search to determine that. So this is decidable. Likewise, if I change A to an NFA, change L of A is equal to 0 to not, equal to empty sets to not, and to not be empty set is also decidable. Okay, so this is NE, okay, it's a DFA, I'm sorry. So of course, this is just the opposite. This is the complement. NE sub DFA is a complement of E sub DFA. We know that if a language L is decidable, if N, then its complement is decidable. Okay, so that's what we did earlier. Okay, so next we're going to look at whether two DFAs are equivalent. That means that whether they accept the same language. Okay, so doing this is also straightforward because if you are given, let's say, doing here, you are given two DFAs A and B. I want to know whether they accept the same language. Now, of course, I know you may be tempted that you check whether L of B is equal by L of A. However, this could be infinite. This could be infinite, so the Turing machine can only handle finite many things. So then, how you can do it? So the way to do it is that we're going to look at closure properties. Okay, so we're going to look at closure properties for regular languages. So what do we know about closure properties? Okay, so the closure properties we have for regular languages are the following. So we know regular languages are closed under union intersection Canary star so we use this notation, concatenation, complement. And we also know that it's reversal. Okay, so we did that earlier. Okay, so now we use these closure properties, one of these now, we don't have to use them more, to see how, to determine how we can compare two infinite sets, whether two infinite sets are equal or are identical. So the way to do this is, so we take, let's look at this diagram. So for these two languages to be identical, it really means that the union is equal to its intersection. So it means that L of A union L of B, so B L of A intersect L of B. If this is the case, then they are equal. So that really is L of A union L of B intersect. Okay, L of A intercept L of B complement, which then is equal to 0. Okay, so this is a regular. This is a regular. This complement is also regular. And the intersection is regular. So for this regular language, I have a DFA to accept it. So it really is equivalent to see whether that DFA accepts something. And we know that that is decidable earlier. So so determining whether two DFAs accept the same are identical, which means they accept the same language, is decidable. Okay, so now let's look at context-free grammars or context-free languages. Okay, so let's look at this particular theorem. Now, this is actually pretty interesting. Result is not difficult, but it provides something that we will use later. So we define a language A sub CFG, which is a set of encodings G comma X, where G is a context-free grammar that generates X, and then this set of these encodings is decidable, which means there is a Turing machine that on this input always halts, and when it halts, if it accepts this input, that then this X is can be generated by G. Otherwise, if it rejects it, then X cannot be generated by G. So how do we determine this? Remember when we talk about Chomsky normal form or for context-free grammar, Chomsky normal form has the following form. So the star symbol, okay. So actually, I just want to say every production rules is in this form or in this form. So A, B, C are variables, and small a is a terminal. And X doesn't appear on the right side of any production rule. So I just say here. So S does not belong to the right-hand side of any production rules. And the epsilon rule can only be under S. So epsilon rule can only be under S. Okay, so that is, so maybe now let's open up a screen, whiteboard. Okay. So a context-free grammar is in this form. Okay, S does not belong, only appears once at the right-hand side. It does not appear at the right-hand side. So this is a star symbol. And the epsilon rule can only be under S. Can only be under S. So then given a string, let's say x, which is x1, x2, Sn. It means the length of x is n, where each xi is a symbol. Now, to derive this, you must first, this is equivalent to having that you use these rules. Now, each time you use these rules, the first time you use it, it generates two variables. And then each time you use it, you generate one more variable, right? So for instance, A goes to BC, maybe BC, then you go to B, let's say B goes to BB, then, right? So that means that after the first application, each time you get one more variable. So you'll need to get n variables. Then using these rules, you can generate a string of length n. So that means that how many steps you do. So to generate a sequence of variables, of n variables, you need n minus 1 steps. And then after that, you have to replace every variables with a terminal, so which then you have n of them. So that means that you only need 2n minus 1 steps. You can generate x. Hence, we know that we can construct a Turing machine, right? So you have a G, which is a context-free grammar as input. You convert it to Chomsky normal form, and then you have to try all possible sequences. Now, this Turing machine tries all possible sequences of using these rules, but you only apply them for 2n minus 1 times for each possible derivation. So the total number of such derivations, you can think of this as a tree height of the tree, and Chomsky normal form derivation is a binary tree. So you have a fixed height, okay, of course, depending on n. And the number of different trees was finite. So you inspect all these trees to see whether X can be generated. Okay, so hence, this Turing machine always halts because you only inspect a finite finite derivation tree that is a finite. All possible derivation, not a tree, all possible derivations. So for each S, okay, so for each derivation is a binary tree, but you look at all possible such binary trees, and it's finitely many. Now, of course, it's a huge number, but it's still finitely many, depending on your given input G and X. So this Turing machine always halts, and it accepts if an input X. So it accepts as long as X can be derived from G. Okay, so this is decidable. Now let's move back. Okay. Okay, so next, we show that any context-free language is decidable. So basically what we want to say here is that if L is a context-free language, now this would be L, then for any given string X, I want to know whether this X can be, is part of its CFL, or it can be generated by a context-free grammar that generates L. Okay, so now we construct a deterministic Turing machine D in the last slide that decides A sub CFG. Then we construct a new DDMM as follows. Because this time my input is simply X. So the language itself is not part of your the input of your decider. So the input is X. But we know that a given language has a context-free grammar that generates it. So we really want to know that so this M, right? So then it's M on X, so the underlying context-free grammar is G. So this Turing machine M, you have the input X. Okay, I know now it's a D. So this is G is a context-free grammar for L. So then it's M on X. Now we just simulate the decider we looked at earlier on the encoding of G comma X. Okay, and then if D accepts it, so in other words, D accepts it means that it's Chomsky normal form. We check all possible derivations and see whether X can be derived from G. If it is, okay, we know that takes that's decidable. So if it is, so in other words, if D accepts it, so that means X is generated by G, then we let M accept X. Otherwise, if D rejects it, then M also rejects it. So we know that it is finite, well, of course, depending on what your input X is. No matter what it is, okay, M always holds, but just you may take the number of steps it takes depends on G and depends on X, okay. But nevertheless, it always holds, and when it holds, it gives out an answer, whether X is in L or not. So it is decidable. Okay, so likewise, we can do a CFG emptiness testing. What you are given now is a context-free grammar. So now we did the similar thing before for testing the emptiness of DFA, so testing whether the DFA accepts something. So for doing this, okay, we cannot use the closure properties for regular languages because context-free languages are not closed under intersection. Okay, so so we have to use a different way. So what we do here is that we construct a decider R such that on this input, which is encoding of a context-free grammar, we first mark all terminal symbols in G. Okay, so this is alphabet. And then repeat the following until no new variables get marked. So in other words, I just want to know whether there is something that can be derived from S. Okay, so first we have to find out whether all these variables can be reachable from the start state. Okay, so we repeat the following until new variables get marked. So mark any variable A where G has a rule. So if it has a rule, then we mark such variable A. So then, of course, S is marked, okay? And each symbol, okay, so such symbols has already been marked. Okay, so for instance, we first mark terminal symbols, and then of course, so for the terminal symbols, that's already marked, and of course, you will have at least some of these things. So these strings are terminal strings. Then this variable A gets marked. Okay, so you do backward until S is marked. Okay, so that means if the star variable is marked, then except we know that there will be something that can be derived from S. Otherwise, if S is not marked, after we exhausted every single production rules, then we reject. So in other words, this context-free language, this context-free grammar doesn't accept anything. Okay, so that's it for today. So in today's video, we basically went over several examples of decidable languages based on regular languages and context-free languages. Okay, so all these answers are fundamental that we want to know, and they are decidable. Later on, we will see some examples which are on context-free languages, but they may not be decidable. Okay, that's it. That's the end of this video.